This is our 7th podcast on chemical bonding.
Yes.
And today we're getting towards the end. We want to talk about molecular polarity.
Okay.
There's a lot of times some confusion between molecular polarity and a bond polarity.
Yep.
And that's very hard to understand. So pay close attention so that you understand bond versus molecular polarity.
Right. So you can't do molecular polarity without bond polarity, but don't confuse the two.
Right. So as we talk about molecular polarity, let's just do a little review. Molecular polarity is a separation of charge. That means that one side of something has one charge, a positive charge over here, and another side has a negative charge. So that's polarity. It's like a little magnet. Think of it like a little magnet, okay? So here is kind of the way to understand this. Think of polarity as a big topic. There is both bond polarity and molecular. Now, what does that mean, molecular?
Polarity of an entire molecule.
Yeah, so like if we take our example here of this doggy toy right here, this is a molecule with several bonds. It has 4 bonds, each bond having polarity or not, and the whole molecule doesn't have polarity.
Or not.
Or not. Now the bond, the only way you can determine whether the bond is polar or not is by the electronegativity difference, which we learned about in a previous podcast.
Right.
And for a molecule, it depends on 2 things, both the electronegativity, so the stuff that's over here, but number 2, also the shape. That's very important. So it's a combination of 2 things that we've learned before. So to help us understand this, I have an analogy, Mr. Sanders.
Oh, already.
This is, for those of you who are into football, and, you know, I won the fantasy football championship at Woodland Park High School last year.
I haven't watched a professional football game in over 12 years.
Wow. Yeah, well, anyways, this guy's, actually, he got in a lot of trouble because he was mean to some women. But his name is Ben Roethlisberger, all right? He plays for the Pittsburgh Steelers. I think he's on suspension this year because of bad things he did with a woman. Okay, but Ben, maybe that's not the best picture. So Ben, he plays in the NFL. And if you play in the NFL, I'm going to contend that you need 2 characteristics.
Okay.
Number 1, you need to be big.
Okay.
And number 2, you need to be fast.
Okay.
Now, if you're really, really fast, I went to college with this guy, Issa Dauni from Ghana, West Africa. He was about 115 pounds, but he was the fastest man I think I've ever met.
Wow.
But if he went out and played in the NFL,
He'd get crushed.
he would be totally crushed. 115 pounds, yeah,
Right.
it would be ugly. Big.
Big.
If you're really, really big, can you play in the NFL? If you're just really, really
Just big, probably not.
Yeah, you ever watch The Biggest Losers? Some of those guys I'm doubting are going to make it in the NFL just because they're not particularly fast.
Okay.
They're big but not fast. I think you need to be both big and fast
Okay.
to play in the NFL.
All right.
So when I say this, we go back to this chart. You must have an electronegative bond, and you must have a shape that does not cancel out.
Okay. So two qualities.
2
is what
qualities.
we're looking at.
So here's what I said. The polar molecule must have a bond that is polar. The electronegativity difference is greater than shouldn't it be 0.5?
0.5, I think.
0.5. It's kind of in that range.
I've seen it written either way.
0.5, and it must have a shape that does not cancel out.
Okay.
All right, and this we say that where there's a geometric center of positive and negative charge. You'll see that in an example in just a minute. Okay, and you use the shape paper. Now, if you look at the shape paper, let me just give you a couple of hints. On the shape paper, I put the words usually nonpolar. Usually polar. Usually nonpolar. Usually nonpolar. Usually polar. Usually polar.
But the word usually does not mean always.
That is correct.
Be careful.
Be careful. All right, so let's do some examples. Let's do a classic example. Water is a classic example.
Okay.
Now, to do this, you do have to draw the Lewis dot structure. And I will draw the Lewis dot structure of a cup of water.
And I'm going to make some shapes.
All right, so water has this particular shape. Now, the shape, by the way, I'm not going to go into this. You could figure it out from the shape paper. This is bent 104.5 degrees. There are 4 regions, or 4 things, and 2 are unbonded. Now, is the bond polar or not polar? So to do that, I would go back and I would look at this table of electronegativities. Oxygen 3.4, hydrogen 2.2. So this is 3.4 and this is 2.2.
That's
and
a difference
this
of 1.2.
is 2.2. So the difference is 1.2. Now remember, that means is that greater than 0.5?
It is.
So the bond is polar.
Okay, so we've met one of the 2 criteria. We have a polar bond in this molecule.
And the second thing we must check out is the shape. So if we look at the shape paper, you would see that it says, right here, that it is usually polar. And the reason it's usually polar, I should just tell you.
That's actually the wrong one, but that's okay.
I should circle it on.
Yep.
It's usually polar because essentially what's going to happen is the one that's got the higher number gets the ever so slightly negative charge, and then the hydrogen is slightly positive, and you sort of ask the question, where's the center of negative charge? Well, that would be right on the oxygen atom. Where's the center of positive charge? Geometrically speaking, it would be right here. Well, guess what? Those are not in the same place.
Right.
So you have a little magnet right here, therefore that makes it
Polar.
polar. Okay?
Okay.
Let's do another example that we've seen before.
Hey, look. By the way, guys, all the examples we're going to do here are all the ones you saw in the previous lesson. So you could even just go back to your notes and add to your notes so you don't have to recopy everything down again.
All right, so for this one, carbon is 2.6. Hydrogen is 2.2. So this is 2.6 and this is 2.2.
That's a difference of 0.4.
0.4 is the difference. So
That's
the bond,
That's a nonpolar bond.
guess what?
Those are all nonpolar bonds. So since they're all nonpolar bonds, you can't have...
This guy's not big.
Right.
Playing the NFL, he's not big.
Right.
He might be fast, but
Right.
you know what? Actually, he's big and not fast, actually. While we're at that, let's ask the fast question. Let's look at the shape question. So in the shape, since the shape is tetrahedral, that is a canceling shape.
Right. Look on your shape sheet, and it says that the tetrahedrals are usually all
And the reason that is, folks, is each of these are 2.2. So these are the positive ends down here. Each hydrogen is slightly positive. And if you're asking yourself, where's the geometric center of positive charge?
Right
it's in the middle of the carbon. And this is the 2.6. Where's the geometric center in
the negative?
And positive and negative, same place, so they cancel.
Yep.
All right.
Okay.
All right, this next one, NF3. This is a pyramidal shape. So let's check our bonds. So fluorine, I happen to know, is 4.0. Am I right?
How do you know that?
I just do.
Wow.
And then fluorine, nitrogen
is
3. So this is 3.0. So the difference is 1.0.
That classifies as a polar bond.
So it's a polar bond. So the bond, check. Now let's see if he's also fast, if you will.
Okay, so
let's see his shape. So if you look at the shape paper in pyramidal, it says it's usually polar. And again, the reason is that the slightly negative charge now is on the fluorine because he has the higher number, and the center of negative charge is down here, and the center of positive charge is on the nitrogen. Guess what? We have a magnet. So this is polar.
Yeah.
No, I probably didn't say this or write this down, but you realize this is nonpolar.
Since they cancel out, that one's nonpolar.
And then the water... Was it the previous one?
Yeah.
This is polar. Probably should just write that down. Now I think about it.
Should.
All right.
All right. From here on out, we will. Okay.
All right. This one, OF2. Well, F we just termed was 4.0, and this is 3.2. I'm starting to do this from memory. It's
3.4.
3.4. So the difference is 0.6. That's good
so
enough.
it's polar. So we've got the bond.
So the bond, check. And then the shape is bent 104.5.
Those are
that's
usually polar.
Yep. And this follows the same strikes as water.
Same as water. Yep.
So this one's polar. So it's got he passed the bond check and the shape check.
Okay.
And then for sulfur trioxide, we're going to do the bond check and then the shape check test.
All right. So bond first.
So this is 3.4. And sulfur is 2.6. 2.6. Well, that difference is 0.8.
0.8. So it passes the bond check because it's greater than 0.5.
Check. But the trigonal planar. When you're trigonal planar, guess what? The shapes cancel out. See how that's kind of symmetrical?
Yeah.
And so it does not pass the shape test, so this is nonpolar.
Right. Guys, look for symmetry. If it's symmetrical, including the unbonded pairs, you have to consider those.
That's right.
If it's symmetrical, if the same thing, if you will, is coming off the sulfur, so we got oxygens coming off the sulfur, those are all the same. It's symmetrical, it's going to be nonpolar.
All right. Sulfur dioxide? Okay, so sulfur dioxide, it's the S and the O. So the bond check, because it's the same bond, it's a check. But the shape test,
notice it's not symmetrical. Sulfur here has two oxygens, but it also has this unbonded pair. An unbonded pair of electrons is different than an oxygen.
See, the center of negative charge would be here. So each of these oxygens have a negative charge. So geometrically, the center is here. The center of positive charge is here, so that causes it. So this passes both tests. Therefore, it's polar. And I think we've got a couple more examples. I2. Now, this one's linear diatomic, but it's the same atom. The bond check.
Negative.
Negative because I don't even know what the numbers are. We can look them up.
But they're the same.
It's 2.7. So, but 2.7 minus 2.7 is 0.
Anything that has, it's bonded to itself is nonpolar.
So he doesn't pass that test. So,
Right.
and actually the shape test it does pass, by the way, because they're different atoms, and it's just based on the bond if you've got a linear diatomic one.
Yeah.
And then HC, and this is the interesting one.
That's fun.
So let's talk about the bond test. Oh, we've got kind of a weird deal here.
Hydrogen's 2.2.
This was 2.2. This was 2. Carbon is 2.6.
Nitrogen's
And
3.0.
nitrogen is 3.0. So the difference here is 0.4, and the difference here is 0.4.
Okay, but
So this is a check. Well,
look at the overall thing.
yeah.
2.2 to 3.0.
Yeah, because really between here and here, though, that's a 0.8. So this
Interesting.
actually does pass the bond test because you look at the external atoms. So this is a bit tricky, but you go back, well, it's linear diatomic or triatomic, and on your shape paper it says that it is usually nonpolar. Guess what? This is polar. Because on the shape, because this is such a higher number, this is going to be the negative side, and this is going to be the positive side, because the electrons kind of get sucked over to this side because of the higher strength of the nitrogen.
Yeah, higher electronegativity.
Higher electronegativity, therefore, this is polar. So, you have to kind of think it through a little bit sometimes.
Yeah. But if you're stuck and you're either doing a worksheet or doing a test or something, just go with the usually, and you're most often going to be right.
Yeah, so there's some exceptions.
Yeah, there are some exceptions.
And you're
however.
seeing what they are.
So if you want an A, think it through. If you're shooting for the C, just go with what's on the sheet.
Yeah, that's probably right.
In practical terms.
I think that's it.
Whoops.
So the one of the practical applications of this, guys, is when you understand. So who cares if something's polar or non-polar?
Mr. Bergman, is that ice in water or is that water boiling?
Boiling. See boiling point.
That's true.
It's bubbles. Sorry.
Okay.
Yeah, a lot of people have asked that question.
Yeah.
My picture. Oh well. So the more why do we care about polarity? The more polar a molecule, the
Higher.
the boiling point. So if you have something that's got very high polarity, it's going to have a higher boiling point. It makes bonds stronger.
Right. That's like water. We're glad water's polar because we're mostly water. And so since it has a high boiling point, we can go out in the sun and not boil off.
That would be important.
That's handy.
Yeah. Okay. So that's why we care about polarity, and you're going to be asked to determine polarity based on the shapes. Now, when I say something about polarity, I should make a note. You're trying to determine the polarity of a molecule. When I talk about a molecule, that's a nonmetal to a nonmetal.
Right.
So this does not apply to ionic, no, or metallic bonds. So polarity only applies to things that have covalent bonds or non-metal to non-metal. So kind of keep that in mind. Okay, kind of a long podcast, but hopefully you learned a lot.